Okay. Well, I think that we can start. Thank you everyone for being here. Welcome to this new AJS. It's been a pleasure to introduce the speaker of today, Rahul Halder. He's a researcher here in SISSA. He is interested in computational fluid dynamics, model reduction, scientific machine learning applied to PhD. And today's talk is entitled Model Reduction for Cerebrovascular Hemodynamics, POD-Galerkin, Hybrid Physics Informed Development. The stage is yours.
Yeah, thank you, Nico, for the kind introduction. Today, as Nico introduced, I'll be talking about model reduction for cerebrovascular hemodynamics and also other theoretical aspects as well. I will shed light on POD-Galerkin, a hybrid physics informed framework, and data-driven and a few novel data-driven approaches. Yeah. So today's there is a lag. Okay. So scope of today's talk is, in the part 1, I will talk about the problem statement, what type of problem we are going to solve. Second, the POD-Galerkin projection-based ROM for this kind of cerebrovascular system. And a very interesting data-driven approach using randomized neural network, and how physics integration could be very much useful for this kind of neural network. So after that, part 2, some of you are quite familiar with this kind of work I was doing. That how to integrate full order model and reduced order model, which is coming from external solver with any type of neural network, and potential application of future application of this in this kind of biomedical applications. And part 3, I will talk about what are the future directions we can go from this type of work. Okay. So the broad aspect of this kind of cerebrovascular hemodynamics is like this. As you know that in case of when as the blood is flowing through this kind of vascular system, in case of our cerebrovascular system, there are 2 different types of problem that might occur sometimes. The stenosis effect, that vascular system gets shrink, and also there are some bulging effect. So to treat this, so doctors might sometimes want to know what are the wall shear stress and those kind of fluid dynamics parameters, so that they can assess how much force that is getting exerted on the vascular wall. And probably you might have some kind of already data coming from MRI data, which is 4D MRI scan. And if you have some kind of reduced order model, you can couple with this kind of data, and you can get some kind of very accurate predictions, very patient-specific accurate predictions of wall shear stress and other fluid dynamics parameter associated with the vascular system. So this is the computational model that we have. So we have considered this kind of 3D geometry. It's a part of our vascular system. And we have considered incompressible Newtonian approximation with a time-dependent inlet boundary condition, stress-free pressure outlet. And if you want to model it here accurately, of course, you have to use non-Newtonian rheology. Also, at some here you can, it's fine for the cerebrovascular system. It's okay to be in the laminar regime, but you have to specially take care of the pressure outlet. So it will be time-varying outlet instead of this kind of stress-free condition that I have considered here. So, and then I have used finite volume-based approximations, and after algebraically discretizing this kind of governing equations, and that is how we time much, and we get the CFD-based high-fidelity simulations. So what we are going to focus on today is this problem statement, that we have a fluid dynamical system, and we want to train it with some kind of velocity input, and want to predict the flow fields at a we want to predict the flow fields at a new velocity input. So that's the problem statement today. And we'll use different data-driven approaches and also projection-based reduced order model, and also some physics-informed approaches. Yeah. So the governing equations, most of us here are familiar with this kind of POD-Galerkin based reduced order model. However, for those who don't know much about this, we project the velocity field and also the pressure field on the reduced space, and and POD is computed solving this kind of minimization problems. But since it is a time-dependent boundary conditions is available at the inlet, so you have to deal with it with some kind of approach called lifting function methods to homogenize the velocity snapshots. And for the detailed analysis, you can go through this paper. So this kind of approach is considered for the current case. So these are the velocity modes, and the pressure modes are considered. And 3 pressure modes and 3 velocity modes has been very effective to approximate the flow physics. Yeah. And then after doing the Galerkin projections, we get this kind of OD, so which we need to solve to get the complete flow physics. And these are the matrix representations which is obtained from the velocity modes and which is obtained from the velocity and the pressure modes. And as you can see, the velocity field at a particular time step, which is basically the topmost point of the sinusoid that you are exciting, and it is quite well matching with a very minimalistic error. Yeah, and okay. Yeah, so and if you look at the time-dependent flow physics, sorry. Yeah, so yeah, so as you can see, they are quite well agreeing with each other, full order model and reduced order model, both the pressures and the velocity field. Okay, so given so now we look at how to approximate the flow physics using a new type of data-driven approach, which is randomized neural network. So in case of randomized neural network, we only update the output layers. So and it gives you a linear structure for the coefficient beta, which needs to be updated. And it is very quick for getting the results because at the end of the day, you solve a linear system of equations. And as compared to the conventional deep learning approach, it gives a very quick predictions. Similar approach, and as you can, and you will see that inference is extremely good here. So and these are the when training and test data are same. When basically I used multi-harmonic signals, as you know, as I have shown that for the training purpose, I have trained with a signal with different types of frequencies and amplitudes, and test with a sinusoidal signals. And of course, it will be always good if my training and test data are both the same. But challenge is that if I now give it a new type of signals, which is the sinusoidal signals, and it, as you can see, inference is really good. Except the fact for this pressure coefficient, the last mode, except only at the last few extreme points, the results are not that well matching with the actual CFD-based pressure POD coefficients. However, you can say it's a quite good match. And then there is another type of approach similar to this randomized neural network, which is some kind of analogous to recurrent neural network, except the fact that you are only updating the output layers and you are only updating the coefficient associated with the output layers. And here also you can get similar kind of linear system of equations because this nonlinear activation functions is acting on these weight matrix and bias vector which are initially fixed. And again, you can get the solution very fast, and because you don't need to use those kind of optimization machinery used in case of ADAM or other type of traditional deep learning network. And here, if you look at the predictions, when the training and test data are same, of course, very good results, it has to be. But in case of predictions with the sinusoidal signals, it is a very good match. Even in case of randomized neural network, as you can see for the last pressure coefficient, I think it got interchanged. The pressure will be the first, the velocity will be the next. Anyway, so all the extreme points have been well captured. So now the idea is that, which I am pursuing now, is that how do you compute, how do you kind of connect these two, this kind of linear system, the type of neural network with physics-based informations. So one idea is that directly you can integrate the full order system, which is the PD in our case, and also the reduced order system, which is the OD in our case. So yeah, so that's the direction I'm going. So, and it will be again very fast to train, because because at the end of the day you get a global linear system. Even if your governing equation is nonlinear, so in that case you can use some kind of Newton-Raphson methods or Picard iterations. Still, it will be much faster than ADAM. So I am still working on this problem. So I tried with this reduced order system. There is another problem is arising now because the system has become ill-conditioned, say matrix, and the result is not good. But for a very simple system like of Poisson equations, I have been able to capture the dynamics. So here what I have done, this Poisson equation is linearized using finite volume method, which is coming from OpenFOAM. So basically you have a AX equal to B type of system, and your neural network, which is the randomized neural network, which is also another linear system. So, and then combine these two physics, combine these two linear system, you get a global linear system, and you get very exact accurate predictions in a very single shot. Yeah. But the potential of this time, here my input is that X, Y, and S. XY is the spatial location, S is the source term, and output is the temperature, which is inside the Laplacian. So potential application will be if I now give a new S, can it infer for a new source term? So that I have not checked yet. Here both the neural training and test data sets are same. So that's the parameterization effort I am practically doing now. Also time-dependent problem, like we have this kind of biomedical applications. These same problems, however, we'll get a global linear system, and then you try to get it in a single shot. So even if you have some kind of nonlinearity, after discretization you will get a global linear system, and then you have to use Newton methods to solve them. I have also tried it with a nonlinear Poisson equations that also very excellently work. With the Picard iterations, Newton Picard iterations. Yeah. Okay. So the next I will talk about this how to couple physics this kind of gradient-based neural network, gradient-based optimization are used in this kind of neural network, like artificial neural network or LSTM of return, like our typical deep learning network with an external solver, like where like OpenFOAM or something like that, where you don't get to know what is there inside your governing equations. So basically, if you don't know what is the structure of the equation, you cannot include it into your computational graph, and then the optimization machinery won't work well. So I will propose some schemes like how well you can handle those kind of scenario in the context of some benchmark problems. Of course, I have not applied it for that biomedical problems, but I'm planning to extend in that directions. Yeah. Okay. So here, of course, since it is discretized physics-based, it is mesh-based. As I tell you that the typical clean architecture, it falls behind the typical clean architecture, because now you have to give the mesh informations. And you can, of course, you can, that meshless architecture that clean has, that is done. But the advantages are that no dependence on X and T, that spatial and temporal variable dependence are not there anymore. But right now you can exactly use it like a surrogate model, and it is a very good framework for parameterization. And boundary condition, initial condition exactly offloaded to the external solver. Okay. Okay. So also I think I have discussed this part also to you quite a lot of time, but again I am reiterating one more time so that so what is the problem associated when the physics-based residual is coming from external solver? That you cannot compute the derivative with respect to the neural network parameters, which is the P. So the way I have handled it, that I have actually break it into using chain rule, del R by del Y pred and del Y pred by del P, and then del Y pred by del P, it is coming from the neural network, and automatic differentiation based derivative computation could be utilized. And del R by del Y pred, it's a sparse matrix, and it can be computed at every, if not at every iteration, but at a interval of iterations. And now I want to design my L loss in such a way so that I don't have to make any changes within the neural network within my clean architecture at all. So now look at these LDs. I'll show you here LDs. So the architecture look like this. So basically this term 2R del R by del Y pred, it is detached. So when it goes to the back propagations, the derivative is not applied on this. So derivative is only applied on Y pred. So basically if this derivative of this equation become exactly like these equations. So it is very intelligently done that so if this is passed to the back propagations, I don't have to do any architectural change within the neural network, and it must work. And I have kind of tested it, some kind of toy problems, where it is not coming from OpenFOAM, but it is coming from another solver written in PyTorch, but it has been detached from the external solver, that I cannot access it. So it has been done manually, not I am by choice. And as you can see, of course, if you just pass the R square, and of course it will overshoot because it cannot see any architecture at all. And if you implement the loss term that I have told, the way I have told, and it will converge well, and it will give you results. So both the ANN and LSTM of type of neural network can be coupled here. So another advantage again here is that since you don't need to compute derivative at all, and it is always coming from the external solver, and so you can use any kind of architecture, graph neural network, LSTM, ANN, whatever, because you don't need to worry about the internal structure at all. Yeah, okay. Okay, so now let's look at now how can it be used for practical purpose, like if we can couple it with some external solver like OpenFOAM. So then again, my final objective is to compute that del R by del variables, and how can we make it cheap, like how to make it computationally more feasible. So here idea is that how to exploit the governing equations architecture itself, and to get a easier approximation of it's a computational cheap approximation of that Jacobian terms. So as you can see, it's a nonlinear transport equations problem. So basically a initial condition driven problems, and there is the U itself is the variables it is advecting this initial condition which is given on U itself, something analogous to Burger's equation, you can say. And if you discretize it in a implicit way, of course the spatial derivatives terms will be given in terms of n+1, and but OpenFOAM handle it by linearizing the convective term. One of the U is actually considered from the previous time set. And then finally you get the residual AU minus B type of residual. And now this fellow has to be minimized in the physics-based loss term. Okay, so now let's look at how can we, now this is my objective now, to compute this del R total by del U pred for our team. So now as we know that since I am using all first order derivatives, and So an plus 1 is only function of the previous time state, bn plus 1 is only function of the previous time state. And if you do these simple hand calculations, you will see that only the diagonal term will survive, and probably the one term other than diagonal A2 will survive, and rest of the term will become 0. And now you can compute this Jacobian very easily. Of course, you cannot compute that at every iteration of your neural network. You have to do it at certain number of epoch intervals, but the life has become much more easier. Okay. So now this is the error approximation, error results, absolute error results that I have got. So if you add those kind of physics-based that corrections that I have told, so you get a little bit less error, and if you just minimize Ax minus b, you get some higher error. So basically here, why I don't need any corrections at all. Okay, I'm happy with A being bit nonlinear, and I want to minimize Ax minus b, and I'll get my results. So if it is something like highly shock dominated flow, then A will be very highly nonlinear. I might get some issue. But for Vargas equation, this kind of problems, okay, A is mildly nonlinear, and I'm fine with it. So then also you will get results. And of course, if you add additional correction that I have proposed, then also you will get slightly better results. But I am facing some issue here. Basically, I'm trying to minimize Ax minus b using Adam optimization. That's the whole game I am doing here. That it's just minimizing a linear system of equation using optimization. And I sometimes see that it is starting from something 10 to the minus 4 or 5, and it is going until 10 to the minus 7, which I'm not happy about. It could have started from somewhere in the higher number and go down, just like it should properly behave to give me a good results, Ax minus b or something. So this is the problem I am kind of trying to address. Maybe you can fix the optimization algorithm, or you have to precondition the A matrix. But if you can solve this problem, then it's a very huge achievement, and you can couple open form with any kind of neural network. But this kind of issue is always there. And that's why I moved to this kind of randomized neural network. So I don't have to use Adam for minimizing X minus b. That's a linear system. I have a linear system, global linear system solved, that's it. So that's one of my motivation for moving to X minus b. But my collaborator Giovanni wants to move to graph neural network. So there he has to go through, he has to fix this X minus b and this problem. I don't know where from it is coming. Something to do with the A matrix. Yeah. Okay, so now also I have coupled reduced order equations, reduced order system of equation with same kind of neural network. But now question is that, okay, once you project the governing equations on a reduced space, you get this kind of OD, and just simply use it in your neural network. Why do you need this kind of correction and all this? Okay, for this kind of Galerkin projections, it's fine, we get a structured OD. But what if you project discretize first and then project? Those kind of reduced order system, you don't know anything about the internal architecture of the governing equations. So my purpose of doing this job for those kind of reduced order system. For this kind of system, you don't need to worry about anything. You know already the OD and put it into your pin and be happy. But if you project first, or discretize first and then project, then you have to couple the external solver. So here my assumption is that the reduced order physics is detached. Although here I can easily, I have forcefully made it detached for those kind of purpose, but this can happen anyway. So as you can see now, my reduced order system is like this, and it can be represented by this kind of time derivative term and spatial derivative term. And always the focus is as many as possible physics information I should give it to the neural network. So here what I have done is A dot term that I computed from the computational graph. So I did not use any time numerical scheme for A dot. I computed the A dot from the neural network itself, but the spatial derivative stuff I considered it as a detached, and it is coming from the external solver. So here also you can see the two loss term is there. One is associated with momentum and one is also associated with pressure. Also here my objective again, how to do this effectively del loss term with respect to neural network parameter and give a new type of LDs which should go to the backpropagation and which will minimize my loss very well. And I have done some mathematics here. So and I get this beautiful loss term which is now have to go to the backpropagation, so that even if your spatial term is detached, it is coming from external solver, spatial derivatives. I mean, so this term, so there is no spatial derivative, just these other terms other than the time derivative. Even if they are coming from the external solver, you will be fine. And for also same I did for the pressure term of the reduced order term. So, yeah, and these are the results. So as you can see, for kind of that for different viscosity, 0.005 meter square per, just the stability of the reserve by computation. So I don't know why it got accepted in physics of fluids. Yeah, but it is only talking about the stability of the system. I did not see any fluid inside. Which is the red? I'll share with you. It's the stability of random reserve by computation. It's just. Okay.
Thank you. Any other question? Yes, thanks again.